So in this series of advanced data structures and algorithms, in our previous lectures we have looked into greedy technique and its various examples that where this greedy technique is going to be used. Now moving with other techniques of algorithm design, one of the most famous techniques is divide and conquer. Are you able to recall any application or any algorithm which is based on divide and conquer? So I can say yes, there are several examples. One is your binary search, that is divide and conquer. Then you have your merge sort, that is also divide and conquer. And on the similar lines, we are going to have one particular application of divide and conquer today, that is counting inversions. So first of all, let us take a quick recap for divide and conquer, and then we will be moving with our today's agenda, that is the application of counting inversions. So when we say divide and conquer, that means we are actually dividing our main problem into several sub parts, and then we are solving each part recursively. After solving each part recursively, we need to combine the solution to all sub problems in order to gain an overall solution. Now what is the most common usage? As we have seen in merge sort, that there is a problem of size n, we are going to divide that problem into two equal parts of size n by 2 in a general scenario, and then we are going to combine the solutions in linear time. As far as binary search is concerned, there is a little difference, as we are going to divide the problem of size n into two equal parts of size n by 2, but we need to pick one particular problem, either the left side or we can say the first half or the second half, and we are looking our element onto that, and there is no need to combine the solutions in the and there is no need to combine solutions. So basically divide and conquer says you need to divide the problem into several parts, and then you need to look for the solutions. Now going with other applications of this divide and conquer, one thing here which we are going to study today is counting inversions. Counting inversions is let us in order to understand this problem of counting inversions, let us take an example of a similarity matrix. So similarity matrix, let us say for example we are going with movie ranking. So user 1 has ranked some movies 1, 2, 3, 4 till n, and user 2 has ranked A1, A2 till AN. Now we want to find that how similar are these rankings. So in order to find the similarity matrix, we need to look for the number of inversion between these array of two rankings. So I can say movie I and J are inverted if I is less than J, but A of I is greater than A of J. So what does this actually mean? We will be looking into various examples of this counting inversions, where this similarity matrix or this movie ranking is going to be used. So one of the a very famous usage of this similarity matrix is in recommender systems. You all must be aware of that. Netflix basically tries to matches your movie preferences with other. So for example, you as a user 1 are going to rank AN movies, and then Netflix consults the database to find people with the similar taste, so that it can recommend you and other people the movies which they are going to like, or Netflix is going to recommend to you movies that they have liked, and the preferences of these two users, that means the X user and you, is going to be match. So if Netflix is going to do this in an efficient manner, doing this well was worth $10 lakh to Netflix. So recommender systems is one of the very famous usage of this counting inversion problem. So going into the details of counting inversions, let us say we have given an integer array ARR, and the size of the array is n, and we need to find the inversion count in the array. So what is this inversion count? So this, as the term tells, it is going to be a number because we are talking about inversion count. So two array elements ARR of I and ARR of j, they are going to form an inversion if ARR of I is greater than ARR of j and I is less than j. So that means we are going to say that this is an inversion. So inversion count for an array is going to indicate that how far or how close the array is from, maybe from being sorted, or how far or how close that array is from other array. So that other benchmark array, if we are going to take as the benchmark array as the sorted one, so the inversion count will give you the kind of, I can say, index or count of far or being far or of being close to the array, which is from which how far or how close it is from the sorted array. If the array is already sorted, then the inversion count is 0, and if the array is sorted in reverse order, then the inversion count is maximum. So sorted array, inversion count 0, reverse array or reverse sorted array, the inversion count is maximum. Let us take an example. So let us say we have an input array which is 4, 3, 2, 1. Now here you can see that all the elements, if we are taking the benchmark array as the sorted array, all the elements are actually kind of we can say in an opposite order. Rather than being 1, 2, 3, 4, they are 4, 3, 2, 1. So if we are going to kind of implement our inversion counting method or our inversion counting algorithm on this is going to give us an output of 6. So there are total 6 inversion counts in this. Now let us see how these inversions are being counted as, and how are we going to have a count of 6. So inversion count, as I have told you, if ARR of I is greater than ARR of j and I is less than j, we are going to take that as an inversion count. So here is the kind of figure. So our ARR, the input array, is 4, 3, 2, 1. So for 4, the inversion count is 3, because if we are going to compare 4 and 3, then ARR of I, ARR of 4 is greater than ARR of j, while I is less than j, while your 3 is less than 4. So that's a kind of inversion. So we are going 4, 3 is not a correct match, or not a correct order, I can say in layman terms. So that's an inversion count. Then if we compare 4 with 2, again an inversion count will be there. It should be 2 in the earlier place and 4 followed by 4. Similarly, if I am talking about 4 and 1, there is also an inversion count. Looking at this, so total 3 inversion counts for the first element, which is 4. Looking into the next element, which is 3, there will be total of inversion count for 3 will be 2 inversion counts, one when compared with 3, one when with compared with 2, and the next one when compared with 1. All these are kind of not in the correct order, should have been 2, 3, but there is 3, 2, again there should have been 1, 3 in sequence, in the order, but the present order is 3, 1. So the inversion count for 3 is 2. Now coming to the inversion count for 2. For 2 when compared with 1, there is an inversion count, and 1 being at the last position, it is not having any inversion count. So total inversion counts in this, if we are going to kind of count, it is coming as 3 plus 2 plus 1 plus 0, which is nothing but 6. So how this 6 is being achieved, let us see. We have an element 4 at index 0. We are going to compare 3 with 4. There is an inversion because 4 is greater than 3 and 3 is present after the 4. Next we will compare 2, again when compare 2 with 4, 4 is present on the left side of 2. So, there is also an inversion, and again comparing with 1, it is going to give us 4 is greater than 1. So, yes, there is an inversion. So, inversion contributed by the element 4 which is available at index 0 is nothing but 3. Moving on to the next element which is available at index 1, element is 3, we are comparing it with 2. So, 3 is greater than 2, but 2 is available on the left side. So, yes, there is an inversion. Then comparing 1 with 3, again 1 is on the kind of available on the right side of 3. So, 3 and 3 is greater than 1. So, yes, there is an inversion. Inversions contributed by 3 is equals to 2. Similarly, if we talk about the element 2 at which is available at index 2 and compare it with the element which is available on its right, which is nothing but 1. So, 1 when compared with 2, we found an inversion. So, inversions contributed by 2 in number is going to be 1, and element 1 which is available at the last position, which is the index 3. So, no element is available onto the right of 1. So, there are 0 inversions which are contributed by that element 1 which is available at index 3. So, in totality, if we are going to take, it is coming to 3 plus 2 plus 1 plus 0. So, overall kind of total inversion count for this particular array is 6. So, also if we want to look this number of inversion counts for obviously for a smaller array, using the a pictorial manner, we can show that with the help of arrows, that arrows show how many elements to the right are smaller than the current one, those are your inversions. Now, which arrows I am talking about, let us see here this in this figure. So, 4, the right arrow from 4 is going to 3, the right arrow from 4 is going to 2 as well as to 1 as well. So, 3 inversions contributed by 4, then we have an two right arrows arising from 3 going to 2 and 1, and similarly these arrows you can witness downwards, then one arrow arising from 2 going to 1. So, if you can count the number of arrows, that is also 6. So, pictorially we can this is just another way of looking into this counting inversion problem, or this is I can say just another way of determining the counting inversion problem, which is kind of a non-technical way. Yes, I agree, but the point is for the smaller arrays you can use this techniques in order to get a proof or something, I can say. So, we have counted inversions. If we are with the help of a very small example, we have just taken an example of 4 elements and we have counted the inversions in this array. Now, let us try to look for, and the numbers were kind of just opposite, just jumbled up. So, instead of having 1, 2, 3, 4, we had the numbers as 4, 3, 2, 1. So, this was kind of a simpler example. Let us look into another example of this inversion count, in which I have taken total number of elements as 5, and the elements are numbered as 2, 4, 1, 3, 5. So, that means there is no kind of linear order, not even reversed. So, elements are, I can say, arranged in the random fashion. So, in order to find the inversion counts, we need to find all the pairs of I and j, 2 elements, such that I is less than j, but ARR of I is greater than ARR of j. That means the index is less than the element, but the actual element is greater. So, for example, if we are going to take one element which is kind of 2, 1. So, this 2, 1, the pair 2, 1, not the element, but the pair. So, the pair 2, 1, that is going to give us an inversion array, the inversion count. The indexes of 2 is 0, the index of 1 is 2. So, the elements at the index 0 and 2 are 2 and 1, and hence there is an inversion. There is no inversion between 2 and 4, because ideally 4 should be kind of on the right of 2. So, between 0 and 1 there is no inversion, between 0 and 2 the elements at the index 0 and 2, yes, there is an inversion. Then between the elements at the index 1 and 2, which are nothing but 4 and 1. Now, these are also kind of not arranged in the requisite manner, it should have been 1 and 4. So, the element 4 and 1, there is also an inversion. Then the element available at index 1 and index 3, the elements are 4 and 3 and the index is 1 and 3. So, there is also a kind of we can say inversion. So, in this way we are looking for all those pairs of the elements I and j such that these two conditions are being satisfied, which is I is less than j and ARR of I is greater than ARR of j. And if we are going to find any such pair, we are going to have that pair as kind of included in the total inversion count. Now, as I have already told you that inversion count, having inversion count as 0 means array is already sorted, and whenever I am saying that array is kind of reverse sorted, we can have maximum inversion count happening when the array is reverse sorted. Fine. So, is it just to kind of gauge the or measure the sorted degree of sortedness of an array? Is it really important, or what is the significance of this algorithm, what is the significance of this technique? Now, first of all, by this technique, that if inversion count equals to 0 implies that array is sorted, and if maximum inversion count is there, that means array is reverse sorted. This technique is useful in calculating how far the array is from being sorted, and all those applications of sorting algorithms and competitive programming. One of the examples I have given you in the inception of this lecture, which was of kind of Netflix. So, yes, they are going to count the inversions between the two arrays, because how far one array is from the another array is going to give Netflix an approach or an idea of the differences into the likings of two different users, and the array here is having different likings. We understood the problem, we looked into the applications or usage scenarios of those problems, that particular problem, sorry. And now moving further, we are going into the solutions of this problem. Now, there can be few solutions to this problem, or there are few we can say methods through which this problem of inversion counting can be solved. So, here within this topic we are going to look into two different algorithms, although there are some data structures which can be used for kind of this in order to solve this problem of inversion counting, but here we are looking on the algorithm itself, not on any specific data structure. So, there are two kind of approaches, two solutions to algorithms. One is an naive approach, which is going to use two nested loops, and because of these two nested loops, the complexity of this is going to be order n square, and the space which they are this method is going to use is order 1 space. Another approach in the line is an expected approach, which is using we can say a modified merge sort, and if we are going to use merge sort, the complexity of merge sort is n log n, but the space, as you all are aware, that merge sort is an algorithm which is looking for an space which is equals to the size of the original array. So, order n space is something which is kind of required when we are using an expected approach, that is using merge sort. The time complexity is order n log n, and if we are going to use the naive approach, which is having two nested loops, order n square is the complexity, but the space is order 1. So, as usual, our kind of, we can say, the trade off is between the time complexity and the space complexity. Now, after looking into the problem, we are going to look into these methods one at a time. Let us begin with the naive approach, which is using two nested loops and giving us a complexity of order n square. So, these two nested loops are basically going to traverse through the array for every index and find the number of smaller elements on its right side in the array. So, this can be done using a nested loop. So, for example, we are going to take one particular element. For that element, we will be looking into the number of smaller elements on its right side. So, one swap through an array, or one we can say traversal through an array. Then the next traversal is to be done for the next element, then for the third element, and then for the fourth element. So, this idea is going to use a nested loop, and finally, whenever we are having these number which is or whenever we are encountering the smaller element on the right side, we are going to increment a particular count, and at the end of the algorithm we are going to sum up the inversion counts for all the indices in the array, and obviously we are going to return the sum, because that is our kind of inversion count, which is the count which we are looking for. So, basically you can say checking each and every element, that how many inversion counts it is contributing, by looking into how many smaller elements are present on the right side of the array, is actually a brute force method for inversion count. So, brute force method is it's kind of simple to implement, intuitive also. So, all the possibilities or all the pairs are to be checked, all the pairs ij are to be checked such that I is less than j, and we need to count how many times ARR of I is greater than ARR of j. So, for this we need to loop over each element with index I, and for each I we loop over all the elements to the right. So, j is greater than I. If ARR of I is greater than ARR of j, then we are going to count this incident as an inversion for I. So, this is what our brute force method, we can say a simple and intuitive method. So, we will run a loop from 0 to n minus 1, select an element in the pair, index j should be greater than index I inside the loop. We will run another loop from j to I plus we will run the another loop, that is j from I plus 1 to n minus 1, and if within this second loop we are encountering an inversion, we are going to kind of increase the count of the inversions by 1. So, here is a pseudo code which is going to explain this method which I have just told you. So, we have count underscore inversion, in which that is the name of the function. We have passed the array, and the length of the array is n. Initially the count is equals to 0, and for every element, for every I in the range n, now for every j in starting from I plus 1 to n. So, the first element will be compared with from second to n and so on and so forth. The second element will be compared starting from third to n and so on and so forth. So, here you can see the two loops, one is for I, one is for picking the element, and another one is for the kind of comparing it with the next element. So, for I in the range n, for j in the range starting from I plus 1 to n, we are looking if ARR of I is greater than ARR of j, that means there is an we can say inversion. So, here we are going to increment the value of count by 1, and this is done by writing the statement count plus 1 equals to 1, or we can say count is equals to count plus 1, and at the end of the count of kind of function, we can say we are going to return the count. So, if we talk about the time complexity of this, very straightforward and simple, 2 loops, 2 nested loops, so complexity is going to be order n square. So, with this huge complexity, I can say this naive method is certainly not suitable for the large arrays, but yes, it works fine for the small input sizes, or when we say when your time complexity or when your performance is not very critical. We can also use this method for learning and debugging when our input size is small, as in we can say whenever n is less than 1000, or we can also use this method for quick prototype or validation of a more optimized algorithm. So, here in this lecture we looked into a new problem of counting inversion. We have established that as a application of divide and conquer. We looked into what is this counting inversion problem with the help of a couple of examples, and in order to solve this problem we have looked into the naive method, which is the brute force method of solving this problem, giving a complexity of order n square. We are yet to kind of explore the more optimized method of doing so, the more optimized method of counting inversions, that is yet to be covered in our next lecture. Here is a list of references which is being used for the preparation of lecture. I will see you in the next one. Till then, take care. Goodbye.